All right, for 2.2, we're going to talk about transforming data. So you're going to be able to talk about how adding and subtracting a constant is going to transform your data, how multiplying and dividing will do it, and then what happens when we do kind of both. Okay? So it is sometimes useful to transform data when analyzing the distribution of a quantitative variable. So for example, maybe you want to convert the units. Maybe you have kilograms and you need pounds, or maybe you have Fahrenheit and you need Celsius. Or maybe you were measuring something and you find out that the machine you were using to measure is messed up and you need to add a constant to every number in order to fix everything. So these kind of things are possible whenever we're doing data analysis. We might need to do some of this stuff. So we're going to talk about how does that transform the data overall. So the effects of adding and subtracting a constant, that's what we'll talk about first. So let's say, for example, there are 30 students in Miss Lakey's statistics class. She gives them a test that's worth 50 points, okay? Here's the dot plot of the student's score along with some numerical summaries. So we see down here that we have the mean, x bar, that's 35.8. We have the standard deviation of 8.17. We know the minimum number. We've got quartile 1. We've got the median. We've got quartile 3, maximum IQR range. So we have all the data we could ever need. Suppose that Miss Lakey wants to be nice and add 5 points to every student's test. What's going to happen? So what we can do is we can basically think about what's going to happen if I take, so this kid who got a 48 and I add 5 is just going to add 5 to his test score. So he's going to go from a 48 to a 50, whatever that was, 52 or 53, sorry. All these kids who got a 45, if I add 5 to their scores, then we're going to be at a 50. And so everybody is just going to move up by exactly 5 for every single number, right? So this guy who got a 25 has now got a 30. So we're just moving every number up by exactly 5. So from both the graph, so here's the graph here, we can see what happens. If we just increase everything by 5, the entire distribution looks exactly the same. It's in the same pattern, same shape, same everything. We're just increasing everything by 5. So let's see what that does to our statistics. So we can see that the measures of center, the mean and the median, and the other measures of location are increased by 5 points. So if we look at our mean here, it was increased by 5. So if you think about that balance point of this distribution, let's say we balance it right here, then obviously all we're doing is we're moving that balance point up to right there. So we're increasing that balance point by 5. Our median also moves up. It goes from 37 to 42. And any other location, so minimum, quartile 1, quartile 3, maximum, all of those things, I just increased all of that by 5. But what about the shape of the distribution? If I look at the shape, it looks exactly the same. So the shape is still a left skewed distribution. And the values for our variability did not change either. So look at our range. Our range was 36 before. It's still 36. So that's because, remember, variability is how spread out the data is. When I take all this data and I shift it all up 5, my spread of my data did not change. It's just now in a different location. So my IQR, which is a distance from the Q3 to Q1, that distance doesn't change, okay? My Q3 moved from 41 to 46, but the distance from Q3 to Q1 is the same no matter if I added 5 or not, okay? So what this tells us is that our locations are going to change, but our variability is not changing. So let's summarize that. As the previous example shows, adding the same positive number to each value, all it does is it shifts the distribution up to the right. If I were to subtract a positive number, then that would just shift all of the numbers in the distribution down to the left. And so adding a value, we're going to call it A. We're going to call it a positive number A. Adding A will add A to all measures of center and other measures of location. So your mean, your 5-number summary, all of those things are going to change by that same factor or by that same addition. So basically when I add a value to my distribution, I add to all of my measures of location. It does not change measures of variability, my range, my standard deviation, my IQR, and it does not change my shape. My shape is still the same, I'm just moving the location of all of the data. So that's what happens when we add. Now if we subtract, same thing, I'm just moving the location, I'm just moving it down. So adding and subtracting, this is what happens. Alrighty. So let's look at an example. Soon after the metric system was introduced in Australia, a group of students was asked to guess the width of their classroom to the nearest meter. Shown below is a dot plot of the data along with some numerical summaries. The actual width of the room is 13 meters. We can examine the distribution of students' errors by defining a new variable as follows. Error equals their guess minus the 13. Note that a negative value would indicate that a student's guess for the width of the room was too small. So these are the student's guesses, okay? The guesses, so a student guesses 10, for example. If I subtract 13, I'm going to get a negative 3. That means the student underguessed by 3. A student who guessed 20, however, if I subtract 13, I get 7. That means the student overguessed by 7. So negative numbers are going to mean that the student's guess was too small, okay? So what shape would the new distribution have? So if I transform this distribution by moving everything down 13, what shape would this distribution have? Well, it's going to have the exact same shape. Every number in this distribution is going to move down by 13. So it's all going to just shift down by 13 and none of the shape would change. So the shape would stay the same, which is approximately, what would you guys think? Right skew? Approximately right skew. And definitely this is bimodal. So that shape's not going to change. All right. What would happen to the mean and the median? So let's think about the mean and the median. If I take this entire distribution and I shift everything down 13, then guess what? That's going to take my balance point, which is currently at 16.02, and it's going to shift it down by 13. So my new mean would be 16.02 minus 13, which would be 3.02. The median, same thing. If I take that median of 15 and I subtract 13 from that number, then I would get a new median that would be down by 13. So my median would be 15 minus 13, which is 2. So those are my new mean and median. Find the standard deviation and the interquartile range of the distribution of error. So my current standard deviation is 7.4. That tells me my average distance from my mean. Okay, so that's my average distance from my mean. If I take this entire distribution and just shift it down 13, this average distance doesn't change. I'm just taking this whole distribution and just moving it down. So my standard deviation would not change. I would still have the same average from the middle of the distribution. The IQR, same thing. If I have an IQR of 6, that tells me the distance of my middle 50%. If everything is moving by the same amount, by 13, then I'm still going to have the same amount of between the data that's in the distribution. So my standard deviation is still 7.4, and my IQR is still 6. And they do not change with transformations of addition or subtraction. And here we have a picture and the summary statistics to confirm that we got our answers correctly. So what about the outliers? So if I have outliers, which I can find that by using the 1.5 IQR rule, I do have 4 confirmed outliers, 27, 35, 38, and 40. Again, when I move all this data down, I'm still going to have the same distance for my IQR. So the IQR test is going to, the 1.5 IQR rule, I'm still going to be identifying the same numbers that are 1.5 away from Q3 and 1.5 away from Q1. So it ends up that while the location of those data points are different, they are still outliers, just like they were in the original distribution. So the same individuals will still be outliers in the distribution. It's just that their values will decrease by 13. So my original outlier of 27 is now 14. My original outlier of 35 is now 22. 38 is now 25, and 40 is now 27. All right, now we're going to talk about what happens when we multiply or divide by a constant. So suppose that Ms. Lakey wants to convert her students' test scores to percentages. Because the test was worth 50 points, she multiplies each adjusted test score by 2 to get the student's score out of 100 points. So if they got a 50, they now have 100. If they got a 40, they now have an 80, and so on and so forth. Below are the numerical summaries and graphs of the adjusted scores and the double scores, okay? So these are the adjusted scores, meaning those are the scores that I added the 5 points to because, I was feeling nice. So we've got our adjusted 5-point distribution, and then we will double those values so that we can get the percentages, okay? So from the graphs and the summary statistics, we can see that the measures of center, location, and variability have all doubled, just like the individual data values. So let's kind of analyze what just happened here. So we took our mean and we multiplied by 2, which takes our 40.8, which is here, and it moves it doubles it to 81.6. Also, what you can see is that our minimum of 17, when we double it, it goes to 34. And our maximum of 53 goes all the way up to 106. And you can already see that the range has increased considerably. And by how much? Well, in fact, it has doubled. So when I multiply, I am spreading that data out. I'm taking lower numbers and moving them up, but not as much as when I take bigger numbers and multiply by a constant. And so my numbers are going to become way more spread out because of the fact that I am multiplying by a number. Same thing would happen with division, except it would shrink the distribution. So I would divide by a number, and that would shrink everything down. And so my original mean would be divided. My range would be cut in half or in thirds or whatever it is that I'm dividing by. Okay. Again, we can also see that our range is doubled, our IQR is doubled, our maximum value got doubled, everything is getting doubled here. My standard deviation gets doubled, my mean gets doubled. So the cool thing about multiplying and dividing is I don't have to worry about it. I just do exactly what it tells me to. I multiply by 2, I divide by 7, I do whatever it tells me to, no matter if it's the location, the variability, mean, standard deviation, IQR, it doesn't matter. Multiplication and division, I just do exactly what it tells me to do, and I call it a day. Okay, I don't have to worry about which one's really changing and which one isn't. So from the graphs and the summary statistics, we can see that the measures of center, location, and variability have all doubled. All have doubled, just like the individual data values. But what has not happened is that the shape of the two distributions is the same. Multiplying and dividing is not going to do anything to the shape. It just stretches or compresses the data. So that top graph, that adjusted graph, I do have a left skew. And whenever I multiply by 2, I just stretch the left skewed out. And so they're both still left skewed, even though one of them is just more stretched out than the original. All right, so let's summarize this. Whenever we are multiplying or dividing each data value, we're going to call this positive number B. We will multiply or divide each measure of center and location by B. We're going to multiply and divide measures of variability by B. The only thing that is not affected is the shape. When we're multiplying and dividing, the only thing that is not affected is the shape. So let's look at an example. The graph and numerical summaries here describe the distribution of the Australian students guessing errors in meters when they tried to estimate the width of their classroom. Because the students are having some difficulty with the metric system, it may not be helpful to tell them that their guesses tended to be about 2 meters too high. So let's convert the error data to feet before we report back to them. There are roughly 3.28 feet in a meter. So for the student whose error was -5 meters, that translates to -5 meters times 3.28 feet in 1 meter, and that is -16.4 feet. So that means that a student that was off or under guessed by 5 meters, that is equivalent to being off by 16.4 feet. Okay, which they might understand that better since that's in their natural units. So to change the units of measurement from meters to feet, we multiply each error value by 3.28. So we're going to see what does that do to the shape, the median, and the interquartile range. First of all, the shape. The shape of the distribution we see is always going to stay the same. Whatever the original shape is still the same. So what shape would we have for this new distribution after we multiply? The same shape as the original distribution of guesses. We're still going to have a skew to the right with 2 distinct peaks, so bimodal. That's not going to change. There's nothing I can do to change the shape. All right, let's look at the median. The median of this distribution is 2 meters. So if I take 2 meters and I multiply by 3.28 meters out of 1 foot, then that's going to give me the number of feet. And so we would get, I'm sorry, I mixed up my units here. This is feet and this is meters. My bad. So if I take 2 meters and there's 3.28 feet in 1 meter, there you go, then I would get the new median. So the new median would be 6.56 feet. Okay. Interquartile range. The original interquartile range is 6, and we're going to find the new interquartile range. And so our new IQR, I'm just going to take that 6 meters, which was the original IQR, and I'm going to multiply by 3.28 feet out of 1 meter, and I'm going to get 19.68 feet. So that's my new IQR. So to summarize, the graphs and the numerical summaries below confirm our results. What happens if we transform a data set by both adding and or subtracting a constant and multiplying and or dividing by a constant? Basically, all we have to do is just follow the rules about transforming data that we've already established and then just use the order of operations. Okay, so PEMDAS, we're going to make sure that we multiply or divide first, and then we'll do the addition and subtraction second. So let's look at this example. During the winter months, the temperatures at the Moores, Colorado cabin can stay well below freezing, which is 32 degrees Fahrenheit or 0 degrees Celsius, for weeks at a time. To prevent the pipes from freezing, Coach Moore sets the thermostat at 50 degrees Fahrenheit. He also buys a digital thermometer that records the indoor temperature each night at midnight. Unfortunately, the thermometer is programmed to measure the temperature in degrees Celsius. A dot plot and numerical summaries of the midnight indoor temperature readings for a 30-day period are shown. Use the fact that Fahrenheit equals 9/5 of Celsius plus 32 to help you answer these questions. We're going to find the mean indoor temperature in degrees Fahrenheit. Does the thermostat settings seem to be accurate? Then we're going to calculate the standard deviation of the indoor temperature readings in degrees Fahrenheit and interpret that value. All right, so let's look at this. We're going to find the mean indoor temperature in degrees Fahrenheit. So the mean in degrees Celsius is 8.43. So 8.43 degrees Celsius is our current mean. Okay? And so what I need to do is I need to do this conversion to get to Fahrenheit. So the first thing I'm going to do is I'm going to do the multiplication. So the first thing in this order of operations would be to multiply. When I am talking about the mean and I multiply, it does move the mean. And so I am going to actually take 9/5 and multiply it by 8.43. So this is the original mean. So I am going to take that 8.43 and multiply by 9/5. That's going to move the location of the mean by 9/5. And then whenever we have a distribution and we are transforming it by addition, that also affects the mean. And so I am going to actually add the 32. This is going to give me my new mean for Fahrenheit. So the degrees Fahrenheit is equal to 9/5 of the original mean plus 32. And when I put that data into the formula and I do the calculation, I find that on average, the temperature in the cabin is 47.17 degrees Fahrenheit. Now, he's needing it to be at 50 degrees Fahrenheit in order for the pipes to not burst. So it seems that the thermostat is not keeping the cabin warm enough. The temperature is not warm enough, so thermostat setting seems too low. So he might want to change that out so his pipes don't burst. All right, now we're going to calculate the standard deviation. So for the standard deviation, the current standard deviation, so the standard deviation is 2.27 degrees Celsius, but I want to convert that to Fahrenheit. So I am going to use this equation. Now, for standard deviation, when I multiply, it does affect my standard deviation. It scales it to that particular value. So for my new degrees Fahrenheit standard deviation, I am going to take 9/5 of 2.27. Now, when we do the add 32, adding 32 to a standard deviation does not affect the standard deviation. Standard deviation is the variability. It's how much it's spread out. If I add 32 to everything, I'm not changing how spread out the data is. So I am not going to add 32. I am going to make a little note here that addition does not apply to standard deviation when transforming. Okay, so all I have to do is multiply the 9/5 times 2.27, and I get 4.09 degrees Fahrenheit. And so that is the standard deviation. And I do need to interpret this. So what that means is that the typical variation of temperature is 4.09 degrees Fahrenheit from the mean. So we found that the mean was 47.17 degrees Fahrenheit. And so that varies by 4.09 up and 4.09 down. So sometimes the cabin is going to get 50 degrees Fahrenheit, but sometimes it's going to get all the way down to like 43 degrees Fahrenheit, which would probably be a really big problem. So this definitely is something that would need to be addressed to make sure that the pipes don't burst. All right, let's look at our application problem. Light travels fast, but it is not transmitted instantly. Light takes over a second to reach us from the moon, and over 12 billion years to reach us from the most distant objects in the universe. Because radio waves and radar also travel at the speed of light, having an accurate value for that speed is important in communicating with astronauts and satellites in orbit. An accurate value for the speed of light is also important to computer designers because electrical signals travel at light speed. The first reasonably accurate measurements of the speed of light were made between July and September of 1882 by A.A. Michelson and Simon Newcomb. Newcomb made 66 measurements at the time in seconds that a light signal took to pass from his laboratory on the Potomac River to a mirror at the base of the Washington Monument and back, a total distance of about 7,400 meters. Newcomb's first measurement of the passage time of light was 0.0000248828 seconds, or 24,828 nanoseconds. There are 10 to the 9th, or 1 billion nanoseconds in a second. To keep the numbers manageable, we converted them to deviations from 24,800 nanoseconds. So Newcomb's first measurement is recorded as 28. The minimum value of negative 44 corresponds to a measurement of 24,756 nanoseconds. So that's That's 24,800 minus the 44 nanoseconds. Here is a histogram and numerical summaries for these data. Suppose we convert the passage time measurements to nanoseconds by adding the 24,800 to each value in the distribution. We're going to find out what shape would the resulting distribution have. We're going to find the median. We're going to find the IQR. And then after performing the transformation, we could convert the measurements from nanoseconds to seconds by dividing each value by 10 to the 9th. And we're going to describe what that does to the shape, the median, the IQR, and then we might look at this challenge problem. So first thing, what shape would the resulting distribution have? What shape would the resulting distribution have? Well, if I look at this particular distribution, I can see that it is approximately symmetric and there's 2 outliers. And so remember, shape is not affected by anything we do when we're transforming. So the shape would stay the same. It would stay approximately symmetric with 2 outliers. That's not going to change. The median in nanoseconds. So I'm going to find the median here. This original median is 27, and I need to convert that from deviations to actual nanoseconds. So all we're going to do here is we need to add the 24,800 to this number. So the median, when we do addition, it actually does get the addition. And so our new median would be 27 plus 24,800, and that would be 24,827 nanoseconds. That's how many nanoseconds that median of 27 deviations was. We're going to find the IQR. Now, for this, we were not given the IQR, so we need to actually find the IQR here by doing Q3 minus Q1. So Q3 is 31, and we're going to subtract 24, which was Q1, and so that would be 7. Now, that is 7 deviations from the true nanoseconds. So if I convert to nanoseconds, because that's what it asks us to do here, convert to nanoseconds, then I would need to add 24,800. The thing is that if I add 24,800 to the quartile 3, and I add 24,800 to quartile 1, when I do the subtraction, I'm basically taking off the 24,800 from both. So the difference between them would stay the same. Because this is a measure of spread, addition and subtraction does not affect measures of spread. When I move this entire distribution up by 24,800, the spread of the data stays the same. It's still a distance of 7 between these two numbers. So all I have to do to convert this is add the units of nanoseconds. All right, so we can now change these nanoseconds to seconds by dividing by 10 to the 9th power, which is a billion. The shape is going to stay the same. Shape, same. The center. So if I take the median, okay, if I take this median that we just found up here, this median of 24,827, and I want to divide by 10 to the 9th. Division does affect everything other than shape. So I will actually divide those numbers, and so I would get a new median, sorry, this is down here. I would get a new median of 24,827 divided by 10 to the 9th. I would get 0.0000248 seconds. That's how fast this is going. For the IQR, I will actually divide by 10 to the ninth. Okay, so when I transform by division, I actually do exactly what it says. So I am going to be shrinking this distribution by quite a lot. And so I'm going to divide by 10 to the ninth. And 7 divided by 10 to the ninth is, so my new IQR, it is teeny tiny, 0.0000. That's very small. That is a very small IQR. So the distance between these two are going to be very small now. So that we have shrunk this distribution to be very, very, very skinny. All right, this challenge problem says use this information provided to estimate the speed of light in meters per second. So what we have to know in order to answer that question is how many meters per second. We have to know how far it was, which we do, 7,400 meters, and then how much it is per second. And so it is which that's what we just found, the median here. This is how much it is per second. So to answer this question, I'll just show you what they did. To answer this question, we would take 7,400 meters divided by this really teeny tiny number, and that's going to give us the estimate of the speed of light based on how far the distance he traveled, so it was 7,400 meters, and the how fast it was for that particular travel in seconds. So this is 7,400 meters divided by that really small number, and we get 298,062,593.1 meters per second. And that's pretty good because the actual speed of light is that. Pretty cool. All right, that is transforming data.